Hello, welcome. This is going to be the lesson over accelerated motion. All the previous lessons we've talked about has been whenever an object's velocity has always been constant. In this instance, or in this case, we're going to start talking about, well, what happens if that object speeds up or slows down? In fact, this is going to be the most common kind of motion that we're going to talk about because everything causes an acceleration. When we start talking about gravity, gravity causes an acceleration. So we need to pay particular attention to this section. In this section, we're also going to probably get the most equations that we're ever going to get in a section this year. And the fact that we're actually going to get 4 brand new equations. Actually, make that 5 equations. So we're going to get 5 new equations in this section. So we need to make sure we get those and we get those written down, and so that we can use them later on. All right. When we talk about accelerated motion, we need to talk about what acceleration is. And all acceleration is it's just a change in an object's velocity over a period of time. Now, there's certain aspects about velocity that we can look at as far as changing. Well, velocity is a vector, which means that it has both a magnitude and a direction. So we can either change the magnitude of the velocity, uh, which would cause an acceleration, or we can change the direction of a velocity. So how can an object accelerate? Well, here I have my initial velocity vector right here. So let's say that I'm traveling 4 meters per second to the right. And we'll just assign some arbitrary number to that. Uh, and so we'll just draw that in there. 4 meters per second. And so I'm traveling 4 meters per second to the right. But what I want to do is, well, I want to see, well, what's going to be my acceleration in these cases. So I have all these different changes or final velocities. And so I'm going to click on this one. And so this is my final velocity. So obviously I went from 4 meters per second to the right to something that's smaller, a smaller velocity vector. Now, I'm going to treat this just like I treated the displacement equation whenever I had the change in, and that was the change in displacement, the delta x, but in this case I'm going to use delta v, or my change in velocity is going to be my final velocity minus my initial velocity. And so I'm going to use this equation using the graphical method of vector analysis to determine what my resultant or what my acceleration vector is going to be. Acceleration is a vector, which means that it's also going to have a direction. And that direction is somewhat ambiguous, whereas that we need to look at what's happening before we can determine the direction of the acceleration. With the direction of velocity, it was easy to determine because that was the direction it was moving, or that was the change in the displacement direction was also the direction of the velocity. So in this case, we've got to kind of look at what's happening, whether the object is slowing down or speeding up. So let's go ahead and follow this method for adding and subtracting, and use our methods for adding and subtracting vectors to determine what the acceleration vector is going to look like. So in order to do that, I'm going to come over here and I'm going to grab this vector. And so I start with my final vector, which is this one, the little green one, and I'm going to subtract the initial vector. So what I have to do with this one is I have to flip it. I actually have to go the other way. That way I can just add them together using the head to tail method. And so if I add the head to tail method and I place the tail of my initial vector on the head of my final vector, well, then what you'll see is that I'll get a new vector that looks something like this. And this is my acceleration vector for that scenario where I have this little guy. So I went from the long 4 meters per second to the right, and I seem to slow down to maybe 2 meters per second to the right with this acceleration. So my red arrow there, my red vector, is the acceleration. Let's go ahead and mark that. So that's my acceleration vector. All right, let's move on to the next instance of what I can do. So let me click on this one. Well, now the object obviously is sped up because its velocity vector has gotten much longer. This is still its negative initial velocity. And so if I were to add these two together, head to tail method, I would place that right there. And I would be left with another vector that starts here at the head, at my starting position, which is this location. Uh-oh, I don't know what's happening. Hold on, give me a second. Let's get rid of that. Let's grab another one. And so it starts here and it goes to there. And so now you can see that my acceleration vector is pointed to the right. All right. And then now let's look at the third instance of what I can do right here. So now, now my direction or my magnitude seems to be about the same, but I have obviously changed direction. I went from going straight to the right to down and to the right. And so if I use this same negative initial velocity vector that I had, so my same initial velocity vector that's negative, and I do the head to tail method, well then my resultant velocity or my acceleration vector is going to look like this. And so I can move that over there, and I'll go ahead and mark it. And so there's the acceleration vector for that. So there's three ways that I can actually accelerate an object. I can cause it to speed up, which is in this second scenario right here. I can cause it to slow down, which is the first scenario, or I can just change its direction, which is this third scenario. Okay, now let's move on. Now does the object, how do we determine whether the object speeds up or it slows down? Well, it's kind of, you got to look at what's actually happening, and I recommend that you write this chart down, put it in your foldable so that you can have it, so that whenever it comes time to determine whether the object is speeding up or slowing down, it's right there. But not only that, but if the problem tells you the object is slowing down, well then there's, we need to know by that statement we can tell whether or not the velocity and acceleration vectors are going in the same direction. So what determines whether the object speeds up or slows down has to do with how does the velocity vector direction compare with the acceleration vector direction. So we'll start with this. My velocity vector direction is to the right, and my acceleration vector is to the right. So what's happening is that the object is speeding up and it's moving to the right. What determines my direction of motion is the velocity. The acceleration has nothing to do with that. The acceleration only determines whether it's speeding up or slowing down. Now let's look at another scenario where the velocity is still to the right, which means the object is still going to move to the right. But now the acceleration is to the left. And in this case, because the acceleration is to the left, then the object is going to be slowing down. They're pushing against each other. But the object is still moving to the right because my velocity vector. The velocity is now to the left, the acceleration is to the right. So what do you think is going to happen here? That's right. The object is going to slow down, but it's going to be moving to the left. So the object is moving to the left, but it's slowing down. And then now let's talk about if both of them are pointed to the left. Well, it's going to be speeding up and moving to the left. So the object is going to be going faster in the left direction. Okay, so what you can use this for is if it says the object is slowing down, right, slowing down, these two middle ones, then we notice that the vectors have to be opposite. Okay, that's important because when we go to start putting numbers into our problems, we've talked about the convention where everything that goes to the left or down is negative and everything that goes to the right and up is positive. So if it says it's slowing down, we need to determine that one of those is going to be a negative direction. All right. Okay, now I'm going to skip over that page real quick because I want to talk a little bit more about acceleration before I give you the other equations. Acceleration, like I said, is a vector. So acceleration is a vector. Now what that means is it has a direction. So just like we drew the resultant, and it was the red vectors back here on this page, those are my acceleration vectors, and they point in a certain direction. In this first instance, my acceleration was to the left. The second, my acceleration was to the right. And then in my final, or the last one, my acceleration was down and to the left. So they have a direction. All right. We also give acceleration, or the equation for acceleration. So the equation is acceleration equals the change in velocity over a period of time. So we've seen this kind of equation when we talked about the velocity being a change in position over a period of time. And so this is actually going to turn out to be acceleration, which is given by the variable a, and then that little hat on top tells me that it's a vector, equals my change in velocity. So there's the delta symbol for change in velocity over my time period, t. Now this isn't too useful for us because it doesn't really tell us a whole lot unless the problem actually tells us our change in velocity. Instead, we want to write it as this: our final velocity minus our initial velocity, all over time. Now if I look at this, the units for acceleration can be derived or analyzed through this equation. And so the units for velocity are going to be meters per second. So I have meters per second on top, and then on the bottom I have time, which is measured in seconds. So now I have meters per second, or acceleration units being meters per second squared. All right, so there's the units for acceleration. Here's the equation for acceleration. Keep this equation. All right, you will want this equation for the homework. Now let's go back. There are four more equations that I'm going to give you today. We can describe all types of motion in just these four kinematic equations. All right, and each of them have a certain aspect that is left out because you don't need it, and that's the reason why there's four of them. So we can leave out some things that we're not given or that we don't care about, and we can find all the rest of the stuff that we need to know. The first equation I'm going to give you is going to be that the object's displacement, delta x, is going to be equal to its initial velocity times its time, or the times the time that it's undergoing the motion, plus 1/2 times the acceleration times the time squared. Now this is a squared function, which means it is a polynomial, it is a quadratic function, and so eventually we'll actually use the quadratic equation for it. Not now. When that time comes, I'll let you know. Another equation is that v final equals v initial plus acceleration times time. The third one, v final squared equals v initial squared plus 2 times an object's acceleration times its displacement, delta x. And then the fourth one says that delta x equals 1/2 my initial velocity plus my final velocity times my time. Okay, so these are my four equations. So these four are very important. I'm not going to require you to memorize them, although it will help out a lot because these are your tools for this unit. And these tools will actually be used for the rest of the year. Now let me point out some of the better aspects of these and why we have these four. If I look at this equation, notice how I am missing my final velocity. So I don't need my final velocity. I don't need it for this equation. So I don't need it, and I don't want it, so I don't have it in that equation. If I were to look at this equation, let's change that from there to that. Well, I'm missing my displacement. I don't need it. So whenever I use this equation, I don't need it. I don't need it, and I don't want it. Now, if I'm looking for my displacement, obviously I don't want to use that equation. Here, time. Time is the factor that I don't need or want in this equation if I use this one. And then the last one, I don't want acceleration. I don't need it, I don't want it, so I don't have to use it. So I'll use this equation. So each of these equations are used to determine all the aspects of kinematics. If I don't have one of those aspects, I can use a different equation. Or I can use a different equation to find that one to move on to the next one. Now, these are all derived from the previous equations that we've had, and I will sit down and show you if you want me to, or you can just Google it, and somebody else has already put a video up of deriving these four equations. These equations are very old. They've been around for years, so somebody else has already taken the time to derive them. If you want to look them up, you're more than welcome to, but these are the tools that we are going to be using. Now, I will work some example problems later on, so that you have those, and then we will call it good for now. Be ready to work some of these problems in class.